to talk about the PV. What is the PV panel? Very, very brief about PV, what is PV, and we talked about.
Do you know any resources that we could learn more about space vector?
Space vector? Yeah, I can concept document if you want to. But the one I give you is the simplest one. I upload the paper. Did you see that? We upload it in the website. You know, see the one there. But that one is the simplest space vector. Space vector is not like that. It's a kind of cheated space vector. Right? Somebody asked me about this 115% coming, very coming. You know, I can explain you what it is. You know, now it's very simple. You know, I don't know who asked that question. Somebody asked. I said, if you have a space vector, you need a smaller DC box, about 15% for the same voltage, right? So if you look at it, how it's going to happen, I have to explain it with a real space vector. See, we said a space vector, right? There is a vector, you know, somewhere rotating, you know. If you look at the real space vector system, algorithm is like this. Here's a hexagon. I don't know, maybe one day I start to teach the real space vector. Here, just listen. You don't have to write anything. Just listen what it is. You know. If you look at the inverter, we have a 3 leg, right? Right? How many possible combinations we can have here based on this switch?
Without opening or without shorting?
Yeah, we cannot short it. You know, shorting will lead to the inverter. Sure. We have 3 legs to the power of 3. And then overall 2 to the power of 3 combination. Combination is going to be 8. 8 cases. You know, for example, this one is on all. This one is on. These are one case. All these 3 they are on, which means the 3 bottom one they are off. Or the 3 bottom one they are on, which means this one is off. This one is on. This one is on. This one is on. So you could have overall 8 possible cases. When these 3 they are on, how much is the output voltage? How much is the output? 0. Why? They're shorted, right? Output, not here. I'm saying output voltage. How about when these 3 are 0? These 3 they are on. 0. Again 0. They call this case and this case they call it 0 vectors. You know, if you go look at it, they call it V0. It's going to be 0, 0, 0, or 1, 1, 1. This is basically a status of these switches. You know, 1 means they are on, 0 means they are off. Now, different cases. I don't have it here to see which one is which. You know, I can look at it, but there are going to be 6 more vectors. For example, I'm not sure. This one I think is 1, 0, 0. I believe it's 1, 0, 0. This vector is 2 over 3. 2 VDC, let me tell you. 2 VDC over 3. This is the first. I think it's 1, 0, 0. I can send those ones that are interested. I can send the document on this one, what they are. The same thing here. 2 over 3 VDC, 2 over 3 VDC. All of them, the length is the 2 over 3 VDC.
When you say 1, 0, 0, does that mean just in one row?
This one is on. Yes, we are looking only the top row. You know, this is on, this is off, this is off. So basically, this one is on, this one is on, this one is on. I'll send this document if you want to guys look at it, you know, for those who are curious. So these are 2 over 3 VDC, 2 over 3 VDC, all of them, they are like that. But a space vector, I talked about a space vector, you know, the voltage you need, see, we talked about EDEQ, remember we said before I normalize it, right? If you look at those EDEQ, I have an ED and EQ, right? If I convert this one, use the DQ, I'm going to get my space vector, they call it V. So this vector is a vector like this, is rotating. This vector is rotating, you know what I'm saying? This is what inverter should ideally generate. This is what is coming from the control loop, right? It's this much voltage, this much phase, right? Now, in my system, I have only 8 cases, right? This is like a continuous to digital system. Do I have any vector here to turn it on here? No. I could have only these 6 cases, and these two, they are the same. They are 0 voltage, right? I have basically 7 cases, and if you look at it, I have 7 vectors, right? So what we do here, we do this way. We say, okay, we project this one and this one and this one. And we say, let's project this one here, project this one here. Hey, to have this one, and there is a switching cycle. Every time you switch, you change one of this one is a one switch, right? During that time, whatever is the switch, like for example, you're working with 25 kilowatts, 1 over 25 kilowatts. You should see over that cycle, 1 over 25 kilowatts, let's say 5 milliseconds. This vector is here and during that time, right? So you should translate it, okay, I'm gonna have this one and this one. You can calculate. For example, 2 milliseconds this vector, 3 milliseconds this vector. You know what I'm saying? You do it this way. So you average it out. You know what I'm saying? Because I have only 6 vectors, right? So I kind of average it out. I say, hey, if I have 2 milliseconds of this one, 3 milliseconds of this one, if this one is here, what is going to happen? It's going to be more of this one, right? For example, 4.5 milliseconds of this one, 0.5 milliseconds of this one. You know what I'm saying? So this is the real space vector. I didn't discuss this one in this course because I thought it was a little bit too much to go there. But now, look at here. Just think about this. How about if this vector is here? What's going to happen? We talked about overmodulation, right? This is exactly overmodulation. We cannot go there. We cannot let the vector go there. This V we are calculating. We put a limit on it. You know what I'm saying? What's the limit?
1.
No, not 1. The limit is here. Now you need to know a little geometry. If my vector is inside this not very good circle I draw here, right? I can project it, if for example it's here, I can go with this one and this one, right? I can go this way, right? But if it's outside of this circle, right? I'm in trouble because I don't have enough voltage, enough vectors to build it, right? Because if it's here, see if it's here, what does it say? It says, it's going to be this much, right? And it's going to be, for this case it's okay. For this one it's okay because it's still you have a kind of partial of this voltage, right? Partial you can control it with the time. But you cannot go more than 2, you cannot go full vector. You know what I'm saying? You can have less than that, but you cannot have more than that. So but here see, I cannot take this one, right? What I will do if my vector is going to say, stop it here. Cut, clamp it here, right? Now, I talked about the 15%. Let's look at it. This is the maximum, just I want to tell you, maximum phase voltage we are going to have. Maximum phase voltage. How much is this? Somebody tell me. How much is this? This is a 2 over VDC. This is a 2 over VDC. How much is this one? 60 degree, right? This is a hexagon, right? And how much is this? 30 degree. And in the based on hexagon, if you connect these two, this one is going to be perpendicular to this one, right? So how much is this one? Cosine of 30 times this vector, right? Is cosine of 30 times 2 over VDC. 2 VDC over 3. This is the maximum phase voltage in the space vector. Now let's go look at the sine theta. How much was the max? Phase. Wasn't it VDC over 2 times NA? So this much, right? You have one leg, right? VDC minus VDC, right? So how much is the maximum voltage here? How much is the line voltage? This is the maximum line voltage, right? Let's do the same thing here. You don't need to do that. You can compare the maximum phase and the same thing here. It's the phase, and you can compare only the phase. You don't have to compare the line, you know. I put the maximum line, you know. But now let's compare this. And MA, how much is the MA maximum here? 1, right? This is the maximum possible for the sine PW, right? How much is this one? VDC over 2. How much is this one? Cosine of 30 is the square root of 3 over 2, if I'm correct, right?
Yes.
So basically, let's get rid of this one because this is the same for both of them. This one is going to be 2, it's going to be VDC over the square root of 3. Here is how much? VDC. I put the maximum MA, right? This is the, I cannot go more than this, right? This is the VDC over 2. How much is this one? VDC over square root. Which one is bigger? This one is bigger, right? Just do this. VDC over square root of 3 divided by VDC over 2. Equal 2 over. Can somebody calculate it? I think it's 1. I think I know the answer. It's going to be 1. So let's double check it. No? Yeah. So that's the reason I'm saying. See, I cannot explain it with the method we talked about it, you know, with the, but real space vector is like this. This is the maximum phase voltage you can have. I'll put some document, you know, just for study, you know, it's not part of this course. If you want to see the real space vector, you know, how it does work, you know. But what we did, the good things about this one, you know, over there, the method I explained, we don't have any control on the switching algorithm. So we don't have any control over that. You know, as soon as the control is more than TRI on, less, that's it. Here, this one has a lot, these two vectors here. You can go unsymmetric. See, I don't know, it's up to you guys how much do you want to read about this one. But this two, if we go completely symmetric on switching, it's going to be like what we talked about. But you don't have to be symmetric on the switching. You can make it unsymmetric. You're switching, you're going to get the same harmonic spectrum with maybe like a 40% less switching. You know what I'm saying? You get exactly the same thing you have with a 40% switching. You know, these are a little bit advanced topic. I don't want to talk about it. But my point is, when we deal with the real space vector, you have the flexibility to select this thing. But the way is the best way for you, because I can go, for example, see that my point is here. This one is, I don't know what is this one. Let's say, for example, this is 1, 0, I don't know, I think it's 1, 1, 0. Right? Going from here to here, usually we do this, we want to have the minimum change, you know, we want to have the minimum switch change. Look at here, if I'm going to go to here, from here, I have to go to a 0 state, you know, because I have to end up the same station, because the next one I'm going to implement, I should be able, you know, I should be able again to start from the same, to be able to repeat it, you know. For example, what I do, if I am here, I start from here. I said, okay, 1, 1, 0, go to 1, 1, 1. This is the way I'm going to switch my 0. Go to, no, I'm going to go from, yes, I'm trying to figure out how I'm going to get there. I think that these numbers I'm putting the wrong numbers, you know that. But usually you try to do, for example, you go from this case to this case, there's only one change. See? Only first one is going to change, right? Right? So basically, leg B and leg C, they are not switching, because they are the same, right? I can either use this or I can use this one, right? They are both the 0 vector, right? But this one is better. Why? Because only leg 1 is going to switch, right? But if I use this one, it's going to, leg 1 is not going to switch, but leg B and leg C, they are going to switch. You know, two switching, you know what I'm saying? This is the sequence you use, you know, right? I can put a little bit more documents for you guys, you know, if you want to read it, you know, read it. One more thing, you know, one of my friends here, unfortunately I cannot advise the student for graduate level. He has asked me, he has a fund to support master students for 2 years, 50%. I don't know exactly what that means. I think, but I think it's paid for your tuition and pay a little bit the stipend. If any of you guys, you're interested, let me know. This is for master program or PhD program, not for undergrad. And myself, I cannot, take anybody, but maybe I'll find somebody in the department, I don't know who, whether it be somebody to be advisor, and that way you get the money paid from there. Is one the smart inverter testing verification and all those. I think this is a really tough. If you guys, by any chance you are interested in the master program, just let me know. Those of you that to see maybe I can help, to get at least one student funded for the master. So basically, this one is coming from in the sine PWM, the maximum phase voltage is VDC over 2. When the space vector is VDC over square root of 3, if you divide it, you're going to get here. It means the maximum phase voltage with the same DC box. If this one is 100, if this one can give you 100, this one can give you 115 volts, right? Or you can go opposite. If I want 100, that one has to be bigger VDC. That one could be less DC, right? And I explained that, yeah.
Okay. Let's say the controller you draw over there doesn't have to go like a triangle shape.
No, I'll give you more if you are interested, because that's very. Just I picked something in the middle of a big document, just I explained that part because somebody asked me why 15% more. Just I want to tell that, But if you are interested to know more about the space vector, there's a very good books. There is a very good document I can give you to do that. Those things. I simulated this one with PSIM. Once I'll show you. When you simulate the sine PWM, you'll see how easy is that one. But I'll show you the space vector I simulated with the MATLAB. I think simulate. See how much it's difficult to implement this one. That's the reason I ignored it for this class, because my point is to learn how the inverters are working. These are, they call it switching technique. Lots of people, they write a patent on this kind of thing. If you can come up with a kind of innovative idea, if you can switch less, think about it. If you can switch less, give me the same harmonic performance, perfect. I'm going to go with that. Why? Switch less means less power, right? That's what people they are looking. In GM, my friend, they used to write 50. Some of them they already did worse, but it was like they wrote like 100 patents on different kind of switching algorithm. You change it a little bit this way, you change it a little bit that way. They wrote patents on this one, But this is kind of now a little bit old. It's maybe like 20 years old now, I think the first paper came out, the basic one, 1986. It came out. It was a very popular paper. Everybody was using with this method, And but now it's getting older than 1986. Now we are 30 years old. It's 30 years old, But at that time was really a hot topic. Lots of people were starting to work on this kind of different switching, But it's still for different converters, This is just inverter. They work on the single phase inverter. They work on the DC to DC converter. Lots of those kind of things, They use different switching technique, to improve it. By the way, Arno uploaded it. We are going to have a lab, simulation lab. This is not related to the project, This is a flyback with control loop. We'll talk about the control loop, after we finish the solar panels, maybe next week, and something like that. And we are going to start that part. But right now, I don't want you guys to be worried about the PI values, You just find it out either with the Arno's help or your try and error, to see when a closed loop system they have. I think you're going to start with a single output flyback converter, for example, 115 volt. But the next phase is, in the same homework, is not homework, is I think lab, I should call it something like that. Multiple output. You want to have you have seen in your lab, you have 15, minus 15, you have 5, right? And in all one box. There's not 3 power supply, right? That's a flyback converter with the multiple output, Just you go work on that one, this is a control. Just look at it. And as I said, I don't want you to get to the detail of control. We'll talk about that later. But start to work with this kind of circuit simulation to learn what's the, for example, power supply. They call it power supply. Now let's go back to the solar. I'm not going to spend very much time on the solar cell and how it does work. And to be honest, I don't know what's the physics of that to talk about it. But I'm going to look at it as a system level engineer. I'm going to look at it that way, I want to use this one, I bought a Camry, I want to derive it. I don't care what is happening in the internal combustion engine, right? I don't need to know that, you know. If I know how to derive it, that's enough. This is exactly how we are going to treat the solar. We'll talk a little bit about the how the characteristic is and those kind of things. But if you guys, I think there's a course here. In that, there are lots of courses, I think, on the VLS side, those kind of things, fortunately, here. If you're interested, you can go get that course. They're going to talk a lot about PN junction, I don't know, solar, those kind of things. One of the students last year, he had the course. I don't know what was it. And he gave me a copy of the note, but it was too much. We are not going to talk about that one, how the solar cells work. But in general, you know, we start with this simple model of solar cell. Solar cells, we can model it like this. This is very, very simple. This is the simplest model for solar cells. I'm not going to go into the detail, but there is more complicated, you know, from, if you are interested, I was looking at Power Electronics by Rashid. Is one of the references I gave you, you know. He has a pretty good explanation about the equivalent circuit for the solar cell, if you are interested to know more. It's not that much detail like a solid state, I don't know, physical electronics, but it has a better description at the system level. Me here, I'm going to go very, very short on a model for the solar cell. We use this model for the solar cell. Basically, is a current source. Let's call this one IPH, and this is the ID. The equation here for the I is this part. I is equal to IPH minus I0 to the PQB over KT minus 1. This is the simplest model for the solar cell. What are these things? IPH, they call it the photocurrent. I0 is a leakage, is a diode reverse leakage current or saturation current. Q is the electron charge. Which is 1.6 times 10 to the power minus 19 coulomb. V is this voltage. V is the voltage, whatever voltage we have here, that's the V. And K is the Boltzmann constant. And the value is 1.38 times 10 to the power of minus 23 J over K. And the T is the cell temperature. You know, I saw this number, you know, there's a number in chemistry called avocado number, I think, right? Avocado number. Sorry, avocado number. It was almost 6 point something. 6.23, right? Times 10 to the power of minus 23, I think, something like that. Plus, yeah, so this 23. When I was in, I remember when I was in my bachelor degree, you know, when I was doing it, we have this general chemistry to go to the lab, and we have the lab to, one of the one of the tests was to measure the avocado, I don't know, avocado, I don't know what was the numbers in the lab. And one of the students, one of the groups, they made the numbers, you do some experiments and they go, play with the numbers. They came up with exactly the same number, 6.03 or something times that. And the instructor says, if, what was his name? Avocado? What was his name? Avocado. He said, if he himself comes here, and with this equipment we have here, no way you can measure that number. And how you guys didn't measure that number? That accurate, what I'm saying? And suddenly, this number, you have to many of 25 years ago. Yeah, 25 years ago. So, we don't care really about this model. Just I'm saying this is if you want to know. If you type in Google, you're going to get tons of information about how a solar cell works. But in general, when there is a sun, this one is the main thing. When they build this kind of thing, better panels where they're going to have more voltage. This is like a current source. This current either can go this way or it can go that way. This is how you can control this output current of the cell. Now, if you plot V, no, not V, I, let's call it IPV, and for the voltage, and versus V, this one is going to be basically pretty flat up to somewhere, and it's going to start to drop. This is a character. This is what I need to know about the solar panel. This is a characteristic of the solar cell or solar panel. So when they make solar panel, what they do, they put these cells in cells, right? I'm planning, maybe to take you for the inside the UCSD, they have this microgrid. We'll go there. If you look at the solar panels, they're like this. There's one cell here, one cell here, one cell here, one cell. Basically, they put all these cells in cells. You know what I'm saying? They do this way, and they go on the ribbon. They make all of them in cells. What is the problem with this?
When one is weak.
What?
When one of them is bad, then it's
Well, one of them is bad. What is going to happen? Everybody has to follow that. It's like a group of runners. Think about it. They can walk only in one line, right?
Do they have the protection circuit on?
Huh?
Do they have to bypass protection circuit?
There are many ways, to fix it, but
Do they have to do it?
no, they don't. That's expensive, I say. When a group of runners, they are running together, and they can only go in one line. They cannot go this way or that way, you know what I'm saying? If one cannot run fast, everybody will stop. Maybe when you're going uphill, somewhere in the road, see somebody is driving slowly, and there's I don't know, 2 kilometers of line of cars behind them. That's the bad cell. Now I cannot call it bad cell, but this is a guy is slowing down the system. You know what I'm saying? That's exactly the same problem here. When you put this thing in series, is one of them is not working the way it should, so it's going to affect the performance. Maybe the cells are good. Maybe there's a partial shading. Bird is going to come sit here, right? No, it happens. It's not a problem, real problem. Boom, and power generation is going to go down. You know what I'm saying? I don't know. There is a tree here. It's just shaded this one, partially shaded. So you cannot do anything. The way they are doing it, there are different methods to do. One way is they have an automatic bypass system built in. When this kind of things happen, it's short this one. You know what I'm saying? It's short that this one is out. The bad thing is you lose your cell, it's not there anymore. But the good thing is still the rest they can do whatever they want. You know what I'm saying? That's one way. Other way is they call it optimizer. If you look at this one, they're like this. Basically, if you look at this solar cell, they're like this, right? Now they put a box here, is a small DC to DC converter. And this is expensive, That's the problem, this is expensive. What they do is like, hey, this one can go 10 amps, for example, that's fine. This one can go 12 amps, that's fine, right? There's a mismatch here, right? What is going to happen? The mismatch is going to go through here. 2 amps is going to go through here, right? 10 amps is going to go here. So basically, this one is going to do whatever it can, the best it can. This one can do the best it can. But the problem is you need this box, right? These are costs. They call it cell level maximum power point tracking. We'll talk about this one, maximum power point tracking. But this way, you can maximize each cell by itself. You know what I'm saying? When you do the per panel, when you have a panel like this, you do it per panel to kind of average out. Maybe this one is not maximized, this one is not maximized. You know what I'm saying? Kind of averaging. As soon as you put them in series, it's not going to be as good as just one by one. But another thing is, you have seen there's a panel, there's a company in the area, north of the area in Luma. It's called InPhase. So just check it in Google tonight. InPhase is one of the leaders. They call it micro converter or macro inverter. What they did, they're not doing it per cell because per cell is very expensive. They're doing it per panel. Because if you look at any home, any solar farm, you see this solar panel, there is not one. For homes, maybe at least there is 10, 20. If you go to solar farm, there is, I don't know how many of them, there is maybe 1,000 of them, they're sitting in the solar farm, right? What they do, they put it behind the solar panels. Hopefully we'll go for this visit, I can show you, we have it here. They put one small inverter behind, this is the front. They put one small inverter behind the panel. So this panel, this inverter is going to control this panel. Connected to the next panel. Connected to the basically they do the maximum power point tracking per panel. They call it per panel. Now their business has not been bad, They got public, I think 5 years ago. They were trying to hire me, like it was I think 5 years ago I was in the area, and then I didn't go there. I have made two mistakes. Tesla wants me to go there, and this guy they weren't. I didn't go to any of them. And most they got public, Most they got public, But they have this macro inverters, and they do it per panel. Now let's talk about a little bit more about what's the characteristic of this solar cells and what's maximum power point tracking, and we'll figure out what I'm saying a little bit more. This is the characteristic of the cell, right? This is what we have for this cell here. This is my cell. I don't care what's happening inside this one. I'm looking at this VI characteristic here, right? They call this one I short circuit. This one they call it V open circuit. It's clear. Why short circuit? Because voltage is 0, right? Solar panels, they are short circuit protected, self-protected. If you have a battery, if you close the switch, what is going to happen? Sorry. Maybe by mistake you have, this one has happened to you in your car, you did something wrong. You see, big spark, right? I don't know, it's going to kill the battery, maybe kill yourself also, it's going to burn yourself, But with the solar panel, don't worry, you can show it. The current is going to max, maybe 6 amps, 7 amps, 8 amps, something like that. So it's not going to kill anybody, it's not going to be a huge current. That's a good thing, it's kind of protected, you know what I'm saying? It's not a source, the voltage like a DC source, when you short it, boom, it's going to go crazy, you know what I'm saying? So this is an I short circuit. And this is a V open circuit. If you keep it here open, you're going to have the maximum voltage. Usually all these solar panels, early morning, when you start, because let's say there is no sun, right? So there is no sun, there is no voltage, nothing, right? But as soon as the sun comes up, so you start from here. Because there is no power generation. At least you should get enough voltage to start to generate voltage. So basically you start from here because it's open, right? As soon as you start to operate it, the voltage is going to drop a little bit. We'll tell you why it's going to drop because of the MPPT. But there is a VOC and there is an I short circuit. Now, let's put it here again together. IPV, VP, right? And the characteristic is like this. As I said, this is all pretty flat. I short circuit, V open circuit. In phase 4 of your project, I'll give you a real PV panel, from I think it's from either General Electric or I don't know BP, the one I give you in the project. You know, the parameters are real parameters. This is the real PV panel out in the market. Now, let's look at the output power. Right? How much is the power at this point? What? Sorry. So voltage is, current is 0 here, voltage is, I don't know, the maximum, but still the P is going to be 0, right? Now for the rest, start to, you have a little voltage times this big current, blah, blah, blah. You go all the way, you see somewhere here. Right? This is what you will see in the panel. So you are going to work only at one point, but this is a characteristic of the panel. They call this point, this is the P max, right? They call this one V MP, I think they call it. Yeah, MP. MP stands for maximum power point. And they call this IMP. And this point is the maximum power point generation, right? MPPT, maximum power point tracking. T is for tracking, I'll tell you later, that's the algorithm we're using. But you have a panel up there, and this is a characteristic of your panel. Where do you want to be with this panel? Right? You want to generate the maximum possible power, right? You already spend your money on your inverter, you spend your money on the panel, so why to not get the maximum out of it, right? For the sun we have. Right. Hold on. You are like one class ahead of us while I'm teaching, you know. But that's the intention. I'm just saying what it is. Now we need to get it there. We need to control this one to get to that. So right now you can figure out the goal of this project, phase 4 of project is I want you to work at this point, right? You start from here, like all the PV system. When they are not working, there is no current. You are not here. You are here, right? You are on the right side of the curve, right? And you need to change it, you know, somehow to get to this point. How you can get to this point? I will tell you now. Let me give you a simple example. Very simple example. This is my panel. These are the lead out of this one. And let's say I have a bunch of batteries here. Battery sets. Right? And no bypass. So let's see. Because if I bypass the battery, I'm going to kill it. I don't know, somehow I want to explain it. I don't know how we can do this, but just I want to say it that way. Right? If somehow I can get this battery, let's say this. Now figure it out. Put this one, right? Originally this one is closed. All of them they have this circuit. You know, there's one switch here, one switch here, right? So, and we know, for example, let's put the numbers here. For example, this is 100 volt, right? This is, I don't know, 75, for example, right? This is 75. I want to get to the 75. What I'm going to do? And let's say each battery is 5 volt. I have 20 of them stacked. It's going to go to 100 volt, right? I have 20 of these. So basically, it's going to be 100 volt, right? I want to get to the 75 volt. What should I do? I'm going to take 5 of this one out. I open 5 of this one, right? And I close this one, right? Basically, this one is going to short. So how much voltage I'm going to have here? 75 volt. 75 volt is going to put me at this point, right?
So basically, you are setting that voltage.
I am controlling this voltage. I'm controlling this voltage. So I change my voltage here. I have control algorithm. That's MPPT. They call it MPPT maximum power point tracking. We'll talk about that. I have a control algorithm. This control algorithm will tell me what voltage I should go for, right? In real system, I don't have battery like this. I have a converter. I have a converter is going to do this kind of thing. It's going to change this one. But the control system algorithm tell me, hey, you should work at 80 volts. Because this game is not going to be fixed. The other thing that's going to happen, let's say we have an early morning sun, we have a 10 a.m., we have a 12 a.m., we have a either 3 p.m. It's different. There are different level of energy, right? This curve is going to change. It's going to be like this. We're going to talk about that. There are a bunch of this curve. They're based on what time of the day you are. When you have a bunch of those ones, you have a bunch of this ones also, right? Right? Maybe 10 a.m. you should work here. That's the best place to be. But 11 a.m. so I don't know, you have a better sun. You know what I'm saying? So we're going to be here. So your control system, your algorithm will tell you, hey, now you should work at 80 volt. You should work at 90 volt. You want something automatic. So change this one, track this one. They call it maximum power point tracking. Track this one. There are two different level of tracking. We call this one electrical, maximum power point tracking. What do you mean by what do I mean by electrical? We will change the voltage and those things and we figure out this one, right? What's another level of? And it's expensive. Usually they don't do it. In 90% of the places they don't have that one. They call it 2-axis maximum power point tracking. One axis is electrical. The other one, you look at your if you have a panel and you sit down on the servo motor, right? Morning sun is here. The best place is to be kind of perpendicular to sunlight, right? Sun is going like this, right? If you can go like this, right? You change it. They do it. I say if you go for this trip, not trip, the visit, they have it here. I can show you. So this one is going to rotate like this. I think it's going to go from here to here. So all the time it's facing the sun. But if for example, it's a home, you're not going to put it there. You put it here. So morning is a little bit like this way. Afternoon is later like this way. For example, here from 11 to 2, you have a kind of perpendicular almost to the panel. You know what I'm saying? They call it maximum power point tracking 2-axis. One axis is electrical. Where I am, where I am. I have one of these curves. I want to go to the best point I can stand. The next axis is, hey, I want to get the best of this one. I'm going to tilt my panel, to be facing exactly the sun. You know what I'm saying? For example, in Southern California, they installed almost all the panels southwest, because if you think the sun is coming from here and it's going to go to west, right? So check this thing. When you look at it at home, these are kind of out of curiosity. Look at it, see where they're facing, the panel. If it's a kind of big house, something like a mansion, those things, yeah, maybe they have it a set facing this way, a set facing this way, a set facing this way, because that one is going to get a multi-source, you know what I'm saying? But the regular home, they have only one direction. If you get them, there are 99% of them, they are southwest. Unless there's a limitation because of trees, something like that is blocking them, they have to put it a little bit in a different way. But if there is nothing around them, it's completely open, it's southwest, facing southwest, because it's going to get the maximum power generation. Now, this curve depends to the two parameters. One is, they call it irradiance. Irradiance is basically how much energy we're getting from sun. The unit for that one, I think, is watt per square meter. For example, I don't know, around 11 to 2, you get a better irradiance from sun. The other one is the temperature. So if it's a cold, if it's a hot, if it's I don't know, what do you think? The temperature goes up. Do you think the power generation is going to go up or down? The power generation is going to go down. People maybe think, oh, it's a warmer day, so we have more energy. No, the power generation is going to go down. If you look at the typical curve for this one, it's like this. For different irradiance is like this. finish the story part very soon. We're going to get to calculations. You know? That's the part you have to implement in your control. But you need to know what it is to be able to control it. So, it's like, for example, this one can be bigger than, higher than this one. So you can see here, you know, for example, this is a 400 watt per square meter. This is a 600 watt per square meter. And this is, for example, 1000 watt per square meter. Now, this is a different, they call it irradiance variation, you know, based on how much, you know, sun is using the energy, because watt per square meter, you know. If you have 1 square meter of the solar panel, under this condition is going to generate 400 watt, this one is 600 and all. Now, you can see, look at here, the V open circuit changes, but not that much. It's almost constant. But you can see the I short circuit is very different. Now, if you look at the PPV, this one is going to happen here. Let me just, it's going to happen almost here. This one is going to happen here. We are going to have this one going, for example, this one is going to be like this. This one is going to be for the second one. And the third one is going to be here. See, you're going to have 3 different curves, right? Based on how much you have. And think about it, this thing is changing any second, but the change is big. The change is not big. It's not going to jump every second from here to here. It does if, for example, there is a cloud, suddenly goes away. Yes, if, for example, it will change from here to here. You know what I'm saying? Because there's almost nothing you go there. But in the normal case, if the sun is there, these changes are very gradual. You know, there's all curves in the between. You're going to go all the way. It's like a continuous going up there, right? Your control system, all the time. If you are here, you should work here. If you are here, you should work here. If you are here, you should work here. See? This is the maximum power point. Maximum power point. You know, MPP. We want to be on this curve. You know what I'm saying? Based on, and the control system should find this to be able to generate the maximum power. This is a variation in radius. We could have variation in the temperature also. This is for different radius. This is again 400, 600, and 1000. Right? Now, let's see how it's going to look like if you have a temperature change. This one is going to be no change here, then temperature is changing, but V open set is opposite of this one. For example, this is a 20 degree C, this is a 40 degree C, for example, and this is 60 degree C. Which one is better? Definitely the 20 degree C is going to give you better power. Why? See, for all of them, almost going to be here, right? It's going to be almost here, right? For all of them, almost the current is the same, right? But this one, the voltage is this much. This one, the voltage is this much. This one, the voltage is this much. So this one is going to have a bigger, you know, maximum power, right? If you plot the PPV. If you plot the PPV, it's going to look like this. this one, the maximum happens almost here, right? Usually in this point. And this one is happening here, this one is happening here. Again, this is a 20 degree, this is a 60-degree C, 40-degree C, and 60 degrees. Okay? Again, we want to get this one. This is a locus. We want to track that locus. Sorry, what was your question? The top is 20. Yes, sorry. The top is 20. So now you figured out what's the, you know a little bit about the solar panel. What are the solar panels? Now I need to turn on the laptop and I'm hoping I'm sure they're going to let me my memory stick. This is the last thing. This is here. That's it. There are two methods. I'm going to put this slide, later, upload it to the website. I'm bringing a copy for you because I printed it already. I forgot to bring it. There are two methods to find these points. They call it, there are more than two methods. I'm going to explain two very common methods. They call it perturbation and observation. That's one method. And the other method, they call it incremental conductance. I'll put the flowchart for both of them up there, and I'll explain it how it does work. I explain it how it does work. And if we'll get time, I don't think so today we'll get time, but if we'll get time, we are going to go talk about the phase 4 of the project, but I don't think so we'll have time to do that. For example, for the part I said the PLF is the PLF. The one they're going to assume you have the phase. Some of you will ask about this one. This is how the PLF works. These are all math. We are not going to talk about this one. Don't worry. We're not going to talk about this one, but let's see how it's going to go. That's what you guys are going to do. I'm going to send you to phase 3. I'm going to work on this one. Here. This is what we're going to do. MPPT algorithm. I'll talk about this method first. This is a little bit easier. So guys, this is another one, just to let you know, maybe you hear about this term, they call it anti-aliasing. They call it, that's good to know for more information. They call it anti-aliasing. Think about it. if you are generating power at home, right? You have a solar panel, you are generating power, you are connected to your home and the grid. Somehow the grid goes off. What you guys should do? Yes, you should disconnect. Why? Yeah, because if you don't disconnect, the utility thinks the grid is off, right? And if they are going to, for example, work on it, do something, right? They assume the grid is cold now, right? It's not powered up. But you are there. Somebody go touch the network, grid, you think this is off. It's not, because you are generating. Now, you need to shut down. As soon as the grid is gone, you can still generate power if you want, but you cannot be connected anymore to the grid. They call it, if you're going to generate for yourself, they call it standalone. You know what I'm saying? When you want to generate for yourself, they call it a standalone mode. But if the grid is there, you're connected to the grid, they call it grid tied operation. There are two modes for every inverter. Grid tied and standalone operation. Most of the PVs now installed in the home, they don't have a standalone. As soon as the grid goes off, shut down. There is nothing, But now companies, they're working on it because, hey, we want to support the load for a home, you know what I'm saying? Even the grid is not there, I have power generation, why should I shut down? I can generate some power. And now they're thinking to put some batteries there because you need to have a battery to match the load, Because if you only rely on the solar, maybe you have too much load, you cannot support it. Or you have less load, you cannot consume it. You have to have a battery there to, if you have surplus or deficit, you can use the battery to compensate for that. But when your inverter is working, right, connected to the grid, if the load somehow can happen, capacitor, inductor, or something, is a critical load, isn't the critical load is the one when it has exactly resonant frequency of the 50 hertz or 60 hertz. What is going to happen? Even the grid is gone. You are injecting AC, I'm seeing that voltage, the 50 hertz, 60 hertz, I'm seeing it, this is like a fake, grid, and grid is not there, but your inverter thinks, oh, the voltage is there, I'm going to keep generating power, right? Now there is an algorithm, they call it anti-islanding. Anti-islanding, what it does, it recognizes the fake from the real. What it does, usually is like this. It does a little bit of, they call it positive feedback. It injects a little bit of bad signal, you know what I'm saying? So what is going to happen? If the grid is there, this little bit is not going to do anything to the grid. The grid is pretty strong and signal, you know what I'm saying? Nothing is going to happen. So basically, you inject a little bit of bad signal here. This one. This delta omega. This delta omega is the bad. You try to change the frequency a little bit, you know what I'm saying? You try to change the grid frequency a little bit. Grid is 60 hertz. You try to change it a little bit, but if the grid is sitting there, no way, I'm going to let you change the frequency. I'm 60 hertz sitting here, nobody can touch me, right? So there's no problem. But think about it. Grid is not there. There is a fake grid, right? This guy is start to push it 8.1, 0.2, 0.3, and this guy is not strong to hold it, right? So what is going to happen? They call it frequency drift. Frequency from 60 hertz either start to go, I don't know, 59.5, 59, 50, goes down this way, or it's going to go up. They call it positive feedback. And you have a limit. As soon as you pass, for example, 0.8 hertz, you know what I'm saying, from the origin, if something is wrong, shut down. They call it anti-islanding. If you hear about anti-islanding, it's an algorithm. There are lots of control algorithms in inverter controls and those kind of. Basically, this one recognize grid is there or not. That's very important to know that the inverter should be smart. I said this, or this is a smart inverter. I said, they have all this kind of algorithm built inside the inverter. Most probably the project, I don't know very much about it, is they need somebody to start to verify all these things for this inverter to make sure they do the reactive power support, they do the active power support, they do voltage support, they do the anti-aliasing. These are kind of a smart inverter, report lots of things. It kind of should be fun, It's not design of inverter and control it, but test and verification of this thing, it still should be fun project, to work on. But now let's go back to what we were talking about. Please. Yeah. Two algorithms. Before going through the flow chart, let me explain it here how it does work. The first method, observation, perturbation and observation. And as you can see from the name, you do some perturbation, you perturb, and you look at where you are going. That's what you are doing. How? Let's look at it this way. I'm going to explain the first method. Is a PPV, right, and VP, right? And this is the curve we have, right? You want to go to the peak, right? I'll start from the left side, but usually you start from the right side. But you know, it's looking a little bit better, I start from the left side. Usually, no way you will be here, you know. But just I want to show, it doesn't matter. You are being this side or this side, you should be able to get to this point. Let's say you are here, for example, right? Let's say you are here, right now. We started this point. And let's say, then when you turn on your PV, usually you start from this point. This is the starting point. Let's call it P1 and V1. I'm not going to put it, you know. At this point, you are P1, V1, right? The first time I'm doing this, I do it blindly. You know, either I want to say, see, you know, if I'm going to go here, I don't know where I am. I don't know I'm here or here. Either I should increase my voltage or decrease my voltage, right? To go there, you know, I don't know. If I am here, I should increase my voltage. If I am here, I should decrease my voltage, right? But I don't know where I am the first time. The first time I don't know whether, let's say increase, right? I'm going to go right direction. So we were, for example, we set the voltage of the PV 10 volts, but let's say, for example, here is 16 volts. I say go 1 volt higher, right? I'm going to come here. If I go 1 volt higher, my new point is going to be here, right? Which means this much P2 and P2. Can somebody tell me? The next one I can go smart, you know, is not blind anymore. Can you tell me how?
Compare it. If P is bigger than P1, then you point out.
So say better.
And then also you increase the
Say better. You know, this is like say in the math word. Say in the math. I can formalize it.
P2 is greater than P1.
Oh, we can look at the slope.
So if you look at it, dP, delta P, and delta V, if they are positive, both means you're in the right direction, right? You increase. You increase your V, your P went up. So again, increase it. Right? Go. So basically, the next point is going to be here, right? You're going to end up here, right? The next point you're going to go. You're moving this way, right? Right. I'm gonna just write the steps for this one, but you go the next step. I'm gonna go a little faster, you know, to get to the peak. This is the next one, right? And the next one is gonna be here, right? And these steps are fixed. Right, delta V. You could have a variable step, which is incremental conductance, or we can go with a fixed step. Every time you increase 2 volts, right? 2 volts, 2 volts. What's the bad about this one?
You can pass.
No, you can go with it. It's not slow. You can select the big delta V, so you go fast. Accuracy, right? If I am here, you jump here, right? Jump here is the. I need to, let's say, do it here. I want to make sure. So now, this one, and now here, right? Look at here. What happened? Delta V is positive.
Power went down.
Delta P is
Negative.
negative. So it's hey, you are going wrong way. Go back, right? It says go here. You are increasing the voltage, right? And as soon as you are here, it says oh, dP over dV is negative, right? Here, they were dP over dV was positive, right? So basically, it's now go back. So basically, you're going to go like this. You start to go like, if you have a good system, you're going to go like this, right? How close you are to here is up to your delta V. If you have very small delta V, you could go like this. Basically, here and here, they are the same. if you measure it, if you come to Rhombus, maybe if I take you to Rhombus, we have a solar simulator over there. I show you this one, you can see the controls, we go 99.9% MPPT. Means how much accurate you are to get to that point. Okay. Now, let's put the steps together for this one. So what we are doing, we are changing the delta V, right? We add a step, we measure the delta P, and we figure out if delta P over delta V is positive or negative, right? So we start like this. We said we said V and I sense. Right? Basically VPV and IPV. Sense. Sense means you're measuring this voltage, right? The output voltage and current of the PV, you measure. Now the next one, you calculate delta P and delta V. Right? You calculate delta P and delta V. So if you calculate delta P and delta V, we can calculate sine delta P and sine delta V. Right? Before here I forgot. 0. Select delta V. Right? You should select a delta V. How much is your step you want to go, right? This is 0 step, yes.
Can you just like what you said, adjust the step? Let's say the slope is large, then we give a large step. The slope is small.
They call it variable, step. Yes, that's the incremental conductance. Hold on a little bit. The next one is that's this one. I'll explain how we're going to get that. This is a fixed step. There are some good advantages about this one. This is pretty stable. The incremental conductance sometimes get unstable, but this one is pretty stable. Now you calculate sine delta P, sine delta V. 3. I need to say Vref. Vref is every time you set this voltage, okay, go 5 volt up, 5 volt up. Basically, you are telling your control system to change your Vref, either go up or come down, right? I call it Vref. So Vref new is going to be Vref old. Old, I mean whatever it was the step before, one step before, right? Vref old plus delta V times sine delta V times sine delta V. Basically, this is like the dP over dV, right? If both of them they are positive, means dP over dP is positive, right? So you should increase. If one of them is negative, you should decrease, right? So the new Vref is whatever we had here, right? How much we had here? This much. Delta P is positive, delta V is negative, positive, right? So how much is the sine of delta P? How much is the sine of delta V? 1 and 1, right? Because both of them they are positive. You are increasing the voltage, and the power went up, right? So this one is positive, this one is positive. How much is the new Vref? Oh, whatever it was before, plus, let's say the step is 2 volt, right? Times 1 times 1. So basically increase your Vref by 2, right? So this way you're going to go this way. They call this one observation and perturbation. And after here, step 4, go to 1. Right? Every time we do this one, go back. Check it. Alright? This is one way they call it, I'm not going to write it down because I need to spell it, is perturbation and observation method. Now let's look at this flow chart here, how it goes. The one on the left. See, we are saying stop. Sense VK and IK. This is a digital. I mean sample number K, right? You sense voltage, current. You measure this. Calculate the P, right? P at the time of K, right? We have a sample number 1, number 2, number 3. Every time we calculate PK. right? You're going to implement this one in your simulation. Listen carefully. This is what you should do. Now here I'm calculating pk minus pk1. If they are the same, equal to 0, things didn't go anywhere, right? We are here. We are here. All the way here. If there is no delta p, means you are there, right? One thing I forgot to say, I need to explain how if the curve changes. Now, but no, if you no, come here. Is this one positive? Yeah, basically, this is what I explained over there. If this one is positive, for example, yes. Let's say it's yes, right? The delta p is here. Check the delta v. If delta v is positive, both of them are positive, right? What do you do? Add delta v to the rest, right? If no, if this one is negative, reduce delta v, right? The same thing here. If this one is negative, again look at this one. Is it positive or negative? Do this one, right? And come here. Something I forgot. Let's say suddenly, we have a new curve here. Let me make sure the peak is different. We were here. The system is working perfectly. We are suddenly there is more sun somehow, right? It does happen, you know. Now from here I should go here, right? I should go here. What is going to happen? Look at this. Boom. I'm going to come to this point, right? This curve doesn't exist anymore, right? The sun changed. Now the curve is this. How much is delta v? Negative. How much is delta v? 0. So define the sine function like this. Sine of f,
Oh, there's no g in sine.
is 1 if f, and is 0 if f is less than 0. Do it this way. So in this case, what is going to happen? Is delta p positive or negative? I'm coming from here to here, right?
Negative.
Negative. How about delta v?
0.
We are not changing, right? So basically, delta v, this one is positive, this is 1, this is minus 1, right? What does it say? It says whatever it was before we were here, right? That was the voltage we were working, right? It says whatever it was before, reduce the delta v, right? Reduce the delta v, because this one is positive, this one is positive, this one is negative, right? So what that means? It says go this way. Right? If you reduce the delta v, you may make a mistake, one step. The first one, when you have a big change. Maybe you go this way. That's fine. After one iteration, it's going to correct itself, go back. You know what I'm saying? So it's kind of automatic, automatically correct itself. Goes back over there. But if you're lucky the first time you're good, go directly, you're going to go there. If you're a little bit, in the bad luck, you go one step wrong and come back. Yeah.
So what's like a typical sampling rate for like when it checks?
Typical what?
Like sampling rate for when it's checking?
It's up to the DSP you are using, how accurate you want to follow that. This is there depends on lots of things, but usually, I think in Rhombus you are doing 1 millisecond, I think something like that. I cannot remember exactly. I can check what rate you are using. But when you have a DSP, you can do whatever you want. So you do.
How do we update a new curve?
I didn't update it. That's not mine. This is the sun.
Yes.
Sun changed, right?
How does
No,
system
to exaggerate this thing, let's say you have a panel here, you put the, let's say glass, a little bit, kind of dark, not a lot, a little bit dark, right? So it's kind of filtering, it's reducing the sun goes there. Just I want to show you how this one you can implement it, right? In the company, we have solar simulator. We tell them change the curve, you know what I'm saying? We want to make sure it's working when we are building this product. We have to check this thing. But let's say if you are going to do it, you have a solar panel here, you have a screen here, you make it a little bit dark. So basically your curve is the bottom one, right? So I'm going to take this one out, right? So you are jumping to that, right? That one is not me. Just in my simulator, I'm trying to simulate that one and make sure my control is working, you know what I'm saying? But that one is not under my control. That sun and the environment, it's going to change anytime, right? So that was the maximum power point tracking perturbation and observation. Now let's look at the other method. I want to go over this one and finish it. You guys, can you stay like 5 minutes more? No, we can finish this one. Let me erase over there. This one also is very easy. Yeah.
So the system doesn't respond to curve, but when it updates, if the curve is changing.
Oh,
then
that?
Yeah.
Yes, you are saying during the 1 millisecond you are doing
Right.
using the curve change. Yes, you are right. Your calculation is wrong. But the possibility of that one happening is almost zero. Because yes, if you update it like every, for example, 5 minutes, you are right. The curve changes, right? So this is the same thing for wind power. Wind power is the same thing. Think about it. How this giant wind turbine, not even giant one, they're small one, they're 5 kilowatt. How fast? Because for the wind turbine, the vertical axis is the shaft speed instead of the voltage is the shaft speed. The horizontal axis is the shaft speed. The vertical axis is the power. To think about the reality. How fast a wind turbine, you have seen wind turbine, all of you, right? How fast the speed of this one can change?
Not very
Very,
fast.
very slow. You know what I'm saying? In wind turbine, the time constant even is much slower than the, maybe you can sample every 10 seconds. PV, because the electrical system is faster, you know what I'm saying? Wind turbine is a mechanical system, it's much slower than the wind turbine, with solar PVs. But if, on that 1 millisecond, or whatever, 0.1 second, whatever is your sample, if there is a change, your calculation is wrong. But usually that one is not a problem at all. Let's look at the next method, we call it incremental conductance. Incremental conductance works like this. Let me start first with this. We say P is equal to VI, right? We say P is equal to VI. V can change, I can change. Both of them they can change, right? How much is a dP? Oh, sorry. Is V dI plus I dV, correct? Both of them they can change. At this point, how much is a dP? If dP is equal to 0 means P is equal to P max, right? If dP is equal to 0, means we are there. So what else does it mean?
dI dV of 0.
This one is equal to 0, right? V dI plus I dV. This is a smarter method, you know. That one is kind of a little bit dumb method, you know. Just you change that one and you look at what's happening. But this is a smarter method, I'll tell you. You can select your steps, you know, based on the derivation you are going to see. This one is 0. Basically, I'm going to get to dI over dV is going to be equal to minus I over, right? This is a condition. Now, let's look at this curve here. If this one, so this is here, right? If you are here, we have that condition. But most of the time, you are here or we are here, right? We are going to go this way or that way, right? Now, I feel bad a little bit more. Let's look at this side. What is going to happen? You know, I want to see how much is the on this side. dP, let's say left side. dP over dV is positive. Is that correct? Okay. On this side, dP over dV is negative, right? And here dP over dV is 0, right? That's the middle term. Yeah.
This is a power curve with respect.
Yes, that's a power curve of the panel we have. P, right? So now I'm going to do this one in my algorithm. So we do. So basically, if we calculate this one is positive, so we should go this way, right? We should increase the reference voltage. If this one is negative, we should reduce the voltage, right? Now let's see how we can put it in an algorithm. and using this guy here. So this side, dp is positive, right? So means, I'm talking about the left side. I'm working on the left side, right? This is the left side. Remember, this is the left side I'm working there. It's going to be vdi plus idv is more than 0, right? Basically, di over dv is going to be, di over dv is going to be more than minus I over v, right? Right?
Mm-hmm.
So on the right side of the curve, dp over dv is less than 0. But after, so our dp is negative.
Actually, I should say dp, not should I say d over dv, because that could go this way, it's going to be negative. If you move this way, no, that's why I should say dp go this way. It's not dp. Now, so if you are on this is the left side, right? Left. If you are on the left side. If you are on the right side, you do the same thing. It's going to end up di over dv is going to be less than minus iv, right? So basically, if you measure your di, dv, and d over I, you know where you are. You're on the left or you're on the right. If you're on the left, increase the voltage, right? If you're on the right, decrease the voltage, right? Reference voltage. So this is incremental conductance. So this one is better because you can judge it. See, d over d, d over di. When you get close to this point, they're going to get smaller and smaller, right? So this one is going to help you. Hey, I'm going to get a selected delta v is a kind of a scale by the di over dv, right? So basically, if di over dv is getting smaller, time it by my, for example, delta v. It's going to get smaller and smaller. Basically, you're going toward the middle point, right? With a smaller delta v. Or if you don't want, just put the fixed voltage again. You don't have to do that one. You're going to say, hey, I'm going to select 2 volts is not that big of deal to go either this way or this way. I'm fine with that. I'll put the 2 volts. They call it incremental conductance for this. So incremental conductance, and you can see why conductance, because it's based on I over V, right? V over I is the impedance. I over V is the conductance. They call it incremental conductance. So quickly, let's quick, then let me talk about this one. Oh, I'm really sorry. It's way over. Yeah, come on. I'll talk about the control of this one a little bit later, but now you know how to track the maximum, right? You have the brain to follow the maximum. And I'll tell you in the next class how we did with the power converter. Look at here, this side you guys go think about it. Well, look at over. We have VK, IK, PK, again positive, no, you're calculating this one, 2 cases, you know what I'm saying? Either you increase or you I'll send you this slide, I'll upload this slide, and I'll bring a print of that for next week.